Okay, so today is going to be a little bit of new information. It's going to look familiar to Newton's second law, and this is the last piece of section 2 out of the textbook of chapter 12, and that is how to calculate weight. So as we take a look, we've introduced two terms now, weight and mass. So a lot of times in our everyday language, these get used interchangeably. However, they are not the same thing. And so your mass, that's how much material makes something up. So if you were to go from here on Earth to the moon, the amount of material that makes you up has not changed. Therefore, your mass has not changed. Mass is also known as inertia, and we're going to get into that more with Newton's first law of motion later on. Weight is a force, and that force is caused by that downward pull of gravity. So when you stand on a bathroom scale, what you are measuring is how Earth's gravity is pulling on your mass of your body. And so our weight equation factors in the mass, how much material is made up of something, and acceleration due to gravity. And so when you're on different planets, for example, or bodies in our solar system, if you go from here on the moon, or here on Earth, I really should say, to the moon, you're going to see that your weight changes, but not your mass. So I know this is a little bit blurry, it didn't transition over really well, but you can see that the mass of the individual, no matter where they are at on Earth, on the moon, or out in space, mass remained the same. And so again, the amount of material that made up that individual did not change. The weight, however, you can see that on Earth they weigh more than they do on the moon, and that's because the acceleration due to gravity is greater on Earth than the moon, because the Earth has more mass, therefore a greater acceleration due to gravity. So we have an equation, and like I said, this formula isn't too bad because it's basically Newton's second law rewrote. And so if you take a look at your handout, you're going to find this as well. But what we have is that weight is equal to the mass times the acceleration due to gravity. Okay, and so we can break that down into our variables, and we can say that weight is equal to m multiplied by g. If you remember, this is a lot like Newton's second law. I'm going to just write this up in the upper right hand corner, that F is equal to ma. Well, if you take a look at the right hand side, we have essentially the same things. We have mass and we have acceleration. The only thing that's different is what's causing the acceleration is Earth's gravitational pull. Like I said, weight is a force. So again, if you go to the produce section of a grocery store and you put in a head of lettuce, for example, into that scale to get its weight, you'll see that it accelerates downward. That spring moves, and you can then measure the weight of whatever produce you have. So when we talk about units, we still want mass in kilograms. And because G stands for not gravity, but acceleration due to gravity, so it's still an acceleration, so that's meters per second squared. So that leaves us with what is our unit for weight. We're used to thinking of weight in pounds, but the SI unit that we work with weight in science is newtons, because again, weight is a force. So what I've done is snipped the formula sheet, and so if you go ahead and take a minute to open this up or find yours, this is the second formula. And so it has a lot of that same information as Newton's first or second law and this equation here, but the first equation on this sheet. It does give you a couple pieces of information. So acceleration due to gravity, like I said, changes depending on what body you're talking about, but even it can change a little bit depending on where you're on Earth. your acceleration due to gravity on the top of Mount Everest is going to be a little bit different than if you were at, say, sea level. So the further you get off Earth or higher elevation you get, your acceleration due to gravity changes slightly. So if you take a look right underneath here, there's two important things. So we haven't really used an equation with a constant, so a lot of times, unless it specifies that you're somewhere else, you can safely assume that the problem is taking place on Earth, and this is your acceleration due to gravity. There's another important piece of information up here, and this is this conversion factor. Like I said, we're used to talking about weight in terms of pounds. We're not talking about pounds here, we're going to use newtons. But if you wanted to convert it or change it into a unit that's a little bit more understandable, 4.45 newtons is equivalent to 1 pound. Okay, so these are going to become important as we look at the next few slides. So weight and mass are proportional, so that means that if one goes up, the other goes up. So for example, when you change the mass of something, your weight is going to change, and vice versa. And so again, mass is how much inertia an object has, and weight is the gravity acting on that inertia. So here's some examples working with the equation, and just like we've been doing all along, I'm going to set up a KFPS chart to work through this. So in this first example, we have an astronaut that has a mass of 112 kilograms. I'm going to go ahead and get that put into my formula under my K column. It asks, what is his weight on Earth, where the acceleration due to gravity is 9.8 meters per second squared. So like I said, on Earth, anytime you drop an object, it accelerates at that exact same rate. Like I said, it fluctuates just very, very little, but again, overall, it's a constant here on Earth. So I can go ahead and substitute that in for my G. So that leaves me with what am I solving for, which it asks for what is his weight. So we're using our formula that weight is equal to mass times gravity. I can go ahead and plug in. And again, just like we saw yesterday in my video reviewing the F equals ma equation, acceleration, you do not square the actual value. Again, it's an squared due to the acceleration's unit. So that's my plug-in. So finally, we're left with solve. So this is an easy problem. You just got to multiply it out. So we're going to take 112 times 9.8. That's going to give me an answer of 1,097.6. Again, we're not talking about newtons, or pounds, I should say. We're talking about newtons. And so we get a kilogram meter per second squared, which is a newton. So this astronaut is going to have a weight in newtons of 1,097.6. Again, we're not talking about pounds. The next example, we have a man has a mass of 65 kilograms on Earth. So just like the last problem, I can go ahead and get my information filled out. It asks what is his weight and what is his weight in pounds. So we kind of have two things to work with here. So the first thing is I was only given one piece of information in this problem, and that's 66 kilograms. There's a key word here. Says that he's on Earth. Sometimes problems won't flat out state that they're on Earth. Unless it specifies that you are somewhere else, you can safely assume that it's talking about Earth. So that means that I can use that constant, 9.8 meters per second squared. Formula, it's going to be the exact same piece of information as the previous example. Weight is m times g. The mass is 66 kilograms. G is 9.8. So your last step then is to solve. So the only change from example 1 to 2 is the mass of the individual we were talking about changed. Otherwise, everything else is the same. So we get an answer of 646.8. Again, we get a kilogram meter per second squared, which really means a Newton. Again, this isn't pounds. So it asks for two things. It asks what is his weight, and then it asks what is his weight in pounds. It's been a little while since we've done this, but back on that equation sheet, there was a very important conversion factor. So at the beginning of the semester, we took time converting inches to feet. We did like quarters to dollars, and then we started working on centimeters to meters and other measurements like that. So if you remember to do this, and I'm going to erase a couple of my lines down here to have some space, the first step is to take your given. So we're going to take our given of 646.8 newtons, change it over to pounds. The conversion factor, and I'm going to write it at the top of the slide here, is that 1 pound is made up of 4.45 newtons. So if you remember, to do your conversion, you put your multiply and draw your line. And now we need to go ahead and put in our conversion factor. The unit you have is what goes in the bottom, because remember, when you divide something by itself, it cancels out. So I'm starting with 646.8 newtons. So 4.45 newtons is what will go in the bottom. 1 pound is what's going to go in top. Now, to mathematically solve this, what you need to do, and I would recommend pausing it once I'm done explaining this, see if you get the same answer. But what you're going to do is take 646.8 times 1, which you really don't need to do that step. You are going to then divide by 4.45. So like I said, if you want to take a minute to pause and see what you get for an answer, you should get an answer of 145.35, something around that approximately. Because newtons is in the top and bottom, remember I like to put those slashes through to show that those eliminated because I divided them. And so I'm left with the unit of pounds, lb. Okay, so this is a lot like number 1. The only thing that changed was they wanted us to take it one step further and figure out weight in terms of pounds versus newtons. So the last example for the notes is that a woman has a mass of 55 kilograms on Earth. What is this woman's mass on the moon? So this question is a little bit tricky. It tells us that this person has a mass of 55 kilograms on Earth. And what they're asking us to determine is the mass on the moon. Remember, mass does not change. Weight is what changes. So the force is what changes from one location to another. The mass does not. The amount of material that she is made up of is the same as here on Earth as it is on the moon. So she's made up of 55 kilograms of mass. So therefore, her mass should be 55 kilograms on the moon. So there's no real formal calculation needed here. Her mass is going to be equal to 55 kilograms. Again, mass does not change. But it asks then in B, what would the woman's weight on the moon, where the acceleration due to gravity is 1.67 meters per second squared? Notice that they told us two things. They told us we were on the moon, and they told us the acceleration due to gravity. If you are in another location, the G should be provided to you. Again, if it states you're on Earth or states nothing at all, you can assume safely that you are on Earth. Notice that the acceleration due to gravity is less. So what do you think should happen to the mass of this woman if she's going to the moon where the acceleration due to gravity is less? Remember, these are proportional. So if the G goes down, that means her weight should go down. So we should have a weight less on the moon than what her weight would be on Earth. So we are still solving for weight. So that means we need 55 kilograms for our mass. But G will be 1.67 meters per second squared versus that 9.8. We're still finding weight. So weight is m times g, and we can substitute in. So like the last two examples, all you need to do then is multiply it out. So when we multiply this out, we get an answer of 91.85. Again, we do not get pounds. We get a kilogram meter per second squared, which is a newton. So this woman would weigh 91.85 newtons. If we wanted to take this a step further, we could find her weight on Earth. We would find that again, her weight is less on the moon than what we see here on Earth. So what I need you guys to do now is add these next problems to your note page. What I want you to do is see if you can work out these 3 examples using your formula sheet and these previous examples. And let's see how you guys do with them, because like I said, we're starting to tread into a little bit of new information since we've transitioned into e-learning. Like always, feel free to reach out to me through a Google Hangout message or send me an email with any questions or concerns.